Discovering Connect Object in the Criminal Investigation. I'm Captain François Bouchot, a digital forensic expert in the IT department of the Forensic on Criminal Intelligence Agency of the French Gendarmerie. This article is a collaboration between the forensic units of the French Gendarmerie and the CNRS, Crystal Laboratory. In this article, we present the problem of searching for connect objects at a crime scene. We propose tools for investigative units. Internet of Things is taking place everywhere in your daily lives. This accelerates diffusion is linked to the development of connectivity with new communication protocols on the miniaturization of electronic devices. There is therefore an inflation of the data exchange with the creation of new services. So it's a challenge for digital security on forensics because we are moving from the study of a single object to a set of interconnect objects. IoT opens new opportunities in criminal investigation, such as protagonists or witnesses to the event. It's digitalized life by interconnecting personal and business devices on data. In this graph, we can see a forecast of the development of these new markets. Many companies like Gartner or Cisco foresees billion of object connect. Several real cases incorporating connect objects have recently made the headlines. For instance, the log from a Garmin watch was used to resolve the Paul Massey murder case in Merseyside in UK. In an Arkansas murder case, Amazon Echo Device acts as a witness. In the case of Antonio Ailo, it was the correspondence between the victim's Fitbit data and information from the home automation system that highlights the murder of a woman. Several difficulties can be listed, such as the heterogeneous nature of the device. They are not always visible. Hidden objects are often neither detected nor found by investigators. Without tools, they search for objects by hand. Objects are not streamed continuously for energy consumption reasons. Investigators may therefore meet the presence of communication system. This article deals with the problem of discovering connect objects and their position. We propose several forensic tools to search for connect objects and their location at a crime scene. First of all, the need to detect and locate a connect object, then a description of operational tools developed, finally, evaluation of the forensic tools as part of investigative exercise on feedback in the real case. The need to detect and locate a connect object. For a forensic point of view, the investigators need to know where the trace of an event is available. On the graph, we see potential source of evidence. The first phase is to identify the incidents on the traces present at the crime scene. Identifications therefore involve searching for objects that are related to the incidents. Thus, forensic investigators are well trained to identify and analyze an electronic medium such as a mobile phone or computer. However, IoT devices come in many forms and hide in the environment. So it's complicated for investigators to identify them. In addition, the investigator may only work on information or devices right to the crime scene for legal matters. So an accurate location is necessary. What is it about all these IoT devices? Their ability to communicate. To detect or locate them, we will focus on radio communication, their digital footprint. There are already many interesting work on the concept of indoor or outdoor positioning. In our article, we list some interesting papers on the subject with focus on IoT protocols. Some methods come from the system, and others are linked to the network like connectivity. Our work is focused on the study of received signal strength indicators on the phase shift. The other solutions are more complicated to implement in an operational environment highly constrained. For example, the time difference of arrival requires network synchronization. In our technical solutions, we integrated the physical factors that can impact the measurements, such as temperature, the presence of several floors, the environment, and the characteristic of the antenna. Description of operational tools. The software-defined radio is used to determine the emission present in the study area. It scans the entire frequency spectrum. It determines which ones are used. Depending on the results, you can quickly and passively know if there are active objects on the crime scene. On SDR, we have not developed a software brick dedicated to localization. This choice is motivated by question of cost, of reprogramming, and deployment of SDR solutions for the gendarmerie. Localization is carried out by two dedicated tools, a single receiver or multi-sensor mesh network. Depending on the frequency and protocol you found with the SDR, we will show the most suitable tools. It also offers more precise measurements of the environment. The single receiver is a variant of the SDR approach based on the chip dedicated to a single protocol. A mobile sensor scans the study area over no frequency range. It gives a global picture on the active devices of the same family of protocol. It's made up of 4 parts: sensor, antenna at a fixed frequency, an auto-location system composed of a global positioning system, GPS, accelerometers, and gyroscope, on the operating system on the battery. In your study, we work on high-speed antennas with a large surface grid. To improve efficiency and reduce the target area, the measurement is coupled with information from the network, such as global system for mobile communication and Wi-Fi. We can use a drone with a single receiver to cover large area. The multi-sensor mesh network is based on the static study of a specific area from several synchronized sensors. They have the particularity of belonging to the same mesh network. They are controlled by a central. It is made up of 6 parts: sensor, antennas at a fixed frequency, an auto-location system composed of a GPS, accelerometers and gyroscope, an operating system, a battery, a mesh communication system, and a synchronized model. It's accompanied by a OS3 system dedicated to calibrate the sensor. It captures external information such as temperature, pressure, aperture on the movement, for example. So if we would like to evaluate the different tools, the single receiver is often used when the connect object or the communication protocol is new, such as Wi-Fi or Bluetooth. The multi-sensor mesh network is more complex to implement due to the synchronization problems. However, it gives a precise on-target vision of the infrastructure connect to several protocols on frequencies, no or not. This solution supports proprietary and conventional protocols such as Wi-Fi, Z-Wave, Bluetooth, Zigbee, XBee, Sigfox, LoRaWAN, etc. Evaluation of forensic tools as part of an investigative exercise on feedback in real case. The scenario of this specific exercise concerns the discovery of a corpse in an apartment. It's based on real facts. It's composed by 3 separate rooms, entrance, room 1, a bedroom, room 2, and a living room, room 3. This flat contains many connect objects belonging to several IoT architecture, an home automation system, a smartwatch, health objects, vocal assistants, and several unusual objects. Experimentations makes it possible to study the performance and effectiveness of the proposed solutions. We define 2 measurement criteria. The first is a ratio between the number of objects detected compared to those present. This can calculate the time to search for objects. We perform a first series of measurements with the SDR equipment to determine the use frequencies. In order not to alter the study area, the measurements are made only around the apartment, as in a rare case of investigation. Thus, in this experience, we are not able to discriminate the objects present outside the scene. We carry out a second series of measurements with a single receiver. It's made at different height to integrate the third dimension. Finally, we realize a third series with a multi-sensor mesh network. We position 3 measurement sensors around the experimental scene. A 4th sensor is placed in the center of the apartment. For the last 2 series, we exclude the frequency outside the scene. This exclusion is based on the measurement of the location of emitting source. The analysis is repeated several times over several days with identical climatic conditions. The indoor temperature is 19 degrees on the outside, 7 degrees on average. This graph represents the communication architecture. This object communicates via different protocols, commercial, Wi-Fi, Bluetooth, Zigbee, Sigfox, etc., on owners. So this table is a summary of the measurement carried out with the different tools. The performance ratio is determined by the number of objects detected compared to those present. The efficiency rate is estimated from the duration of acquisition of the objects. We are studying the location accuracy of the measurements. In order to install the 4th sensor of the multi-sensor mesh network, we must enter into the apartment. These actions will generate a Zigbee communication between the opening sensor and the Orvibo hub. This event will be recorded and detected by the network. with a single receiver, we don't perceive this signature, this special signature. We observe that the tool offers the possibility of finding more connect objects than a manual approach. Terralion dots is not detected because Bluetooth communication is only active during manual data synchronization. No communication is detected between the lamp and the Philips Hue kit on its hub. Indeed, this required the realization of an event from the control application on the mobile phone. Since it's based on the Sigfox protocol provide punctual and limit feedback. Thus, detection requires a long measurement over time. A ROSE bracelet is not connected to a network. We cannot detect it. To carry out this statistical study, we examined the last 400 relevant forensic missions to find connect objects. This analysis is carried out over 4 years. The first tables show the use of the tools developed according to the characteristics of the measurement area. Missions without equipment take place mainly in residential area from urban and village environments. It represents 3/4 of the study case. Indeed, the so-called manual method is limited in terms of efficiency for large coverage area with hidden objects. SDI equipment meets the need for broad coverage of the countryside or the forest. It offers rapid resolution of tools, especially in the context of one-site intervention. The single sensor is mainly used in urban and suburban area. It offers general farming with the use of drone. The multi-sensor is used in heterogeneous area. This result is explained by the ability of the tool to cover more different protocol and frequency. Mixed solutions are used in complex environments. They respond of the problem of targeting and covering a large area. The second table focuses on the geographic and climatic characteristics associated by the terrain. The third and the fourth table give the number of radio signal detected and the number of connect objects discovered per mission. The last table shows the performance of the used tools. Percentage referred to the number of objects found with the tools in addition to a manual approach. The law used to assess the add value of the field tools. In these different measurements, we are not able to know the real number of objects present. That the performance ratio between the number of objects found and the real number is not calculated. So, the number of connect objects encountered during a mission can exceed 80 per target. In the absence of tools, the volume of objects found is divided for a coefficient of 2. The question of measurement time is a primordial and incompressible factor in the choice of an acquisition method. This criterion is difficult to quantify and to generalize for all cases encountered by the investigators. It breaks down into 3 stages: a deployment phase of the measurement tool, an acquisition phase followed by data processing, and a device uninstall phase. The installation time for the single received is 2 minutes on average. For multi-sensor mesh network, it takes about 30 minutes to an hour. This time factor will depend on the characteristic of the terrain and the area to be covered. Moreover, it can evolve depending on the addition or removal of measurement devices. The hardware removal time is the same as the deployment time. The data acquisition time in a single receiver is between 10 minutes and 12 hours. On average, it is about 1 hour. For the multi-sensor mesh network, it oscillates between an hour and a week of measurement. The average is 24 hours. Processing is almost instantaneous for a single receiver. With the multi-sensor mesh network, it is 10 minutes. This is when the information is collected, processed, and displayed on the web portal. However, this publication of the result does not take priority over their collection. The accuracy of the measurement is also an important factor in making it easier to find objects in complex environments. It depends on the used software and hardware. For example, the antenna on the single receiver are omnidirectional. Those of multi-sensor mesh network are directional. Thus, the single receiver has an accuracy of 10 meters. The accuracy of the multi-sensor mesh network is about 1 meter. So, to conclude, the rapid growth of IoT poses new security and forensic challenges. Faced with the heterogeneous and hidden devices, detection and tracking tools must be developed to assist investigators. We propose 2 tools based on the radio signature of objects. The use of these tools depends on the device sought, operational constraints, and the characteristics of the terrain. The next stage of this research is to select and collect them. The challenge is to understand the infrastructure of connect objects to optimize the collection method without altering the stored data. This solution must meet the requirements of the field. Thank you for your attention.